Now let me show you the genius of Boneh DeMillo. So this is going to be a little math, but don't worry, it's fun math. It's not bad math, it's good math. So the idea is I have a device, a card, which is going to do, it's a decryption oracle or a signing oracle. I give it plain text and it signs them using RSA with an unknown private signing key. And I know that it's going to do Chinese remainder theorem. So it's first going to do modulo P, and then going to do modulo Q, and then it's going to do the Chinese remainder step together to connect them. And I can create a fault, a transient fault, which ruins one of the two, either the calculation modulo P or the calculation modulo Q. How does it ruin it? I don't really care. This is what's really cool about this thing. It does something. It could do something to the multiplication, could do something to the logic, could do something to the storage. I don't really care. As long as modulo P is broken, and modulo Q is not broken. So let's do this. Okay. So I'm talking about now. Let's say it's a decryption oracle. So I can calculate as an attacker, by the way. Sorry. So the attacker has a decryption box, a decryption oracle. I give this box ciphertext, and I get plain text. Okay, this is a reasonable assumption, and I know the value of n because n is public. Okay, so now I am going to take a ciphertext and give it to the decryption oracle, and I'm going to get the plain text, right? So I gave it C, and it's going to give me M. It's going to work. That's what it always does. So it's going to get me M by using the Chinese remainder theorem. So C to the power of D modulo N, I just showed you in the previous slide, is equal to this. So first of all, it's going to calculate M sub P. Then it's going to calculate M sub Q, which are going to take them a quarter of the time. And then they're going to combine them together using the Chinese remainder theorem to get M, which is modulo N. Yossi Oren is asking something. The same box does M sub P and M sub Q. Doesn't really, it could be softer. You could say that you have like a logic unit which does this and a logic unit that does that. I'll show you the fault attack. It does really. You just need to be able to attack one of them and not the other. You need one of them to be broken and the other one isn't broken. So now the attacker does the fault, and this fault breaks M sub P. So M sub P is now calculated incorrectly. Okay. So the box was trying to calculate C to the power of D modulo P, but there was a fault. So now it's like a random garbage value. And now, after this garbage value was calculated, the box, which is trying its best, is going to combine this broken M sub P with the function with the non-broken M sub Q. It's going to send me this M prime. So it's going to send me M prime sub P times this thing plus M sub Q times this thing. So you see M sub P was broken and M sub Q was not broken because we only got we did the fault attack in half of the system. And now the combination, of course, is also broken because if you take one broken thing and you combine it. So who wants me to explain again what the attacker did to get this result? Should I explain again what did the attacker do to get this to happen? Okay. I'm very, very happy to explain it. So the attacker has a box which gets a ciphertext C and returns the message M. This is what the box does. And how does this box work? It takes C, reduces it modulo P, calculates C to the power of D modulo P, which is M sub P, and then it takes the C, reduces it modulo Q, and creates M sub Q, C to the power of D modulo Q. And these two intermediate operations, M sub P and M sub Q, are combined using the Chinese remainder theorem to get M. This is what the box does. Now the attacker was able to fault, create a transient fault in the box such that C to the power of D modulo Q was calculated correctly. So M sub P, M sub Q is the original M sub Q. But C to the power of D modulo P, there was some error. I don't know what error, but all I know is that M prime sub P is not equal to C to the power of D modulo P. It's some random noisy value because the decryption had a fault. And now the device under test, the box, is going to try to combine M sub P prime and M sub Q. And the answer is not M, because by the Chinese remainder theorem, there's only one value, which is modulo P and modulo Q. And this is the original M, so this is a different one. And now the attacker has M and M prime. And now look at this fantastic thing which the attacker does. This is the Boneh DeMillo Lipton attack. So the attacker calculates this value. Now, before we go into what is this value, let's see what are the operations that the attacker performs. How does the attacker know the value of N? How does the attacker know the value of N? N is public. N is a public key, right? How does the attacker know the value of M? It's a decryption oracle. We gave it C, we got M. How does it know the value of M prime? We do the fault attack, right? We do the fault attack. GCD is a very cheap operation, right? You know how to run GCD. You learned it in school. Very cheap operation. So this operation is definitely doable. It's not really hard to do. And now let's see what is the answer of this calculation. So GCD of N and M minus M prime. So N is equal to P times Q by definition. M minus M prime, if you look at it, you see that M sub Q times P times 1 falls out because it's the same between the two. So this part falls away. And this part is in common. So I get M prime sub P minus M sub P times Q times Q minus 1 modulo P. Some kind of number. Now look at this fantastic thing which happens here. This is something times Q. P times Q. And this is something else times Q. Right? This is something else times Q. So what is the GCD between the two numbers? Q. You see why? This is a multiple of Q, and this is a multiple of Q. Can it be anything else? Could it be a larger number? No, it can't be a larger number because P is prime. So the only two factors here are P and Q. Now, I really want you to understand this. So who wants me to explain again how do you get Q out of this fault test? Who wants me to explain it again? Okay. So I have some people who want to explain it again. M sub M prime has the same calculation modulo Q because there wasn't a fault there, but there is a different calculation modulo P. So when you do the Chinese remainder step, this part is the same and this part is different. When I subtract them, I do M minus M prime, this part cancels out because it wasn't different. And now I get M prime sub P minus M sub P times Q minus 1 modulo P. Now all of this All of these numbers, m sub p minus blah, this is just nonsense. I don't really care what these values are. But this is some multiple of q. On the right, I have a multiple of q. And on the left, I have another multiple of q. This is p times q. And now the Chinese remainder, the GCD algorithm can find out the greatest common divisor. So there are only 3 divisors to p times q. It's 1, it's p, and it's q. 1, p, and q, they're the only divisors of p times q. So this is a multiple of q. So this is something times q, and this is something times q. The answer is going to be q. And this is how we found the key using a faulted. Fantastic, fantastic result.